And we can start, sir. I think most of the people have joined.
Recording in progress.
Okay, so today I would solve a couple of more problems on velocity measurement, and then also maybe one or two problems related to viscosity measurement. So we start with this problem on use of a hardware for a measurement of velocity. So the question says that a hardware operating at a temperature of 200 degrees centigrade and the air temperature is 20 degrees centigrade. The velocity of air may vary between 0 and 10 meter per second. The hardware element is a platinum wire of 4 micron in diameter and 1.2 millimeter in length. And it is saying that what is the sensor output when the air velocity is 4 meter per second. So typically it is saying that the hot wire is operating at a temperature of 200 degrees centigrade. That means it is a constant temperature hot wire anemometer. Constant temperature hot wire anemometer. Hot wire anemometer, and in a constant temperature hot wire anemometer, our output Q should be equal to E square over RW. This is something that we have studied in the class. The heat that is released from the hot wire anemometer is basically square of voltage divided by the resistance of the wire. So basically the voltage output E is going to be the heat released from the hot wire divided by the into the resistance of the wire square root. Okay, so this is going to be the output, the sensor output. Now for that, to determine E, we need to determine the heat that is lost by the hot wire. The hot wire is, as we discussed, it is typically a cylindrical wire, and the ends are basically connected to a Wheatstone bridge. Okay. Something like that. The ends are connected to a Wheatstone bridge. So this wire has a length of 1.2 millimeter, and the diameter of the wire is 4 micron. So in order to find the voltage output, we have to know the heat that is lost by this hot wire anemometer, or the dissipated by this hot wire anemometer. And we also need to know what is the resistance of the wire that is at a constant temperature of 200 degrees centigrade. So as we know, the resistance of a wire is a resistance at a reference temperature into 1 plus alpha times temperature minus the reference temperature, right? And in this case, the resistance of the wire, so we have basically the temperature is known, 220 degree centigrade, right? So we need to find out the material properties of the wire. Let's say this is platinum, right? So for platinum, temperature is at 20 degrees centigrade. From the material table, we can actually find the resistivity at 20 degrees centigrade is 10.5 into 10 to the power minus 8 per degree centigrade. This is a material property and which is a function of temperature. Since the temperature is 20 degrees centigrade, right? The air is moving at 20 degrees centigrade. So your density, the resistivity of the hot wire, the electrical resistivity of the hot wire is 10.5 into 10 to the minus 8 degrees centigrade per degree centigrade. And we also can read the resistance temperature coefficient alpha value, which is typically 0.00385 per degree centigrade. So if we have these two values, we can actually find resistance, because the formula of the resistance at 20 degrees centigrade is the resistivity into L divided by A as per the formula. And resistivity is 10.5 into 10 to the power minus 8. The length of the wire is 1.2 millimeter, that is 1.2 into 10 to the power minus 3 meter divided by area. Area of cross section is pi by 4 into d square. D is 4 micron, 4 into 10 to the power minus 6 square. So if we calculate this correctly, this will come out to be 10.03 ohm. Okay, so this is the resistance of a platinum wire at 20 degrees centigrade. Then at 200 degrees centigrade, this is the reference temperature, right? So at 200 degrees centigrade, what is the resistance of the wire? R20 into 1 plus alpha into T, which is 200 degree, minus the reference temperature, which is 20. So that is resistance is 10.03, 1 plus 0.00385 into 200 minus 20. If we do the calculation, the resistance of the wire will come out to be 7.1 ohm. Okay, so we have found the resistance of the wire. One part is done. Resistance of the wire is calculated. Now we need to calculate the heat dissipated by this cylindrical wire. Now to calculate the heat dissipated from the cylindrical wire, what is the formula? The heat dissipated by the cylindrical wire is H into A into delta T, right? So that is H into area of a surface area of the cylinder is pi d into L, right? Diameter is d, this is d, and this is L. So pi d into L is the surface area of the cylinder, times delta T is basically 200 minus 20, the temperature difference between the wire and the ambient. Okay. So we know diameter, we know length, but we do not know the heat transfer coefficient. So we need to find the heat transfer coefficient. How do we find heat transfer coefficient? To find heat transfer coefficient, we need to use this formula. Nusselt number, the Nusselt number based on the diameter is basically H times D divided by the thermal conductivity. So we need to know all the properties of the air. Okay, thermal conductivity of the air we need to know. We need to also find Nusselt number. So there is a correlation that we can use. Nusselt number happens to be temperature of the wire minus temperature divided by temperature of the ambient to the power 0.17 into 0.24 plus 0.56 into Reynolds number to the power 0.45. So this correlation is one such correlation that we can use, and if I ask you a problem, I will give you this relationship where Nusselt number is related to temperature of the wire and the ambient temperature and how fast the flow is happening, the Reynolds number. So we need to calculate first the Reynolds number. Now Reynolds number is basically V into diameter divided by the kinematic viscosity. This is the definition of Reynolds number. V is known, right? It is, the question says that air velocity is 4 meters per second. Diameter is known. We can read the kinematic viscosity. So for temperature 20 degrees centigrade for air, kinematic viscosity is 24.15 into 10 to the power minus 6 meters square per second. Thermal conductivity is 0.032 watt per meter degree C. So we can first find the Reynolds number. Velocity is 4 meter per second. So 4, diameter is 4 micron, 4 into 10 to the power minus 6. Kinematic viscosity is 24.15 into 10 to the power minus 6. So the Reynolds number will come out to be 0.663. Okay. Now, if you know the Reynolds number, if you substitute here, we can find out Nusselt number. So now the Nusselt number will be temperature of the wire. Now this temperature of the wire is at 200 degrees centigrade. Ambient is at 20 degrees centigrade. So see, TW here is not strictly the temperature of the wire, it is the mean of the temperature of the wire and ambient. So this is 110 degrees centigrade. So this is TW is the mean of the wire temperature and the ambient temperature. So you have 110 centigrade is 273 plus 110 divided by 273 plus 20 degrees centigrade, that is the ambient temperature, to the power 0.17 into 0.24 plus 0.56 into Reynolds number is 0.663 to the power 0.45. If you do the calculation properly, the Nusselt number will come out to be 0.738. Okay. So if Nusselt number is calculated, the heat transfer coefficient, now H, from here, this formula, H is Nusselt number into thermal conductivity divided by the diameter. So 0.738 into thermal conductivity is 0.032. Then D is 4. So that gives you 5906 watt per meter square degree C. So we found the heat transfer coefficient. So if we know the heat transfer coefficient, we substitute here and find out the heat loss. So the heat transfer Q dot from this formula, the heat dissipation can be calculated as pi d into L into H into 200 minus 20. Now if we substitute for everything, H is 5906 into pi into diameter is 4 into 10 to the minus 6. L is 1.2 into 10 to the minus 3 into delta T is 180. So if we do the calculation, this will come out to be 0.016 watt. Okay, so this is the heat that is coming out of the dissipated from the hot wire. So if you know Q, we can find out what is the output. So output is square root of heat dissipated into the resistance of the wire square root. So the output E is 0.016 into the resistance of the wire, that is 0.10 ohm. Square root, thus will give us 0.524 volt. Okay. So this is how you would really work through to calculate the output of a hot wire anemometer. Similarly, if it is a constant current, then in that case the formula will be slightly different, but the methodology will be the same. Okay, so you will take a similar approach of finding out the resistance and finally the current, which is output. Okay, so if everybody is fine, I will now move on to the next question. So this question talks about a time of flight instrument for measurement of velocity. And we have discussed that this works based on the principle of Doppler effect. That means if we have a flow path, something like this, and if we have a transmitter here, and if we have a receiver here, if you have some sound emitted from the transmitter and which is going towards the receiver, if this is going at some velocity v, and if there is flow at some velocity u, then if they are in the same direction, you would see that the transfer of this wave from the transmitter to receiver would basically, the relative velocity will get added up, and the time would be basically, let's say if the length is L from here to here, then the time will be L divided by V plus U. Okay. If the flow is in the opposite direction, it will become V minus U. And based on these two, we can actually determine the velocity with which the flow is going, okay, using suitable electronics. So that is something we have covered as part of the theory. So here we would say, the question says that consider water flowing in a pipe of 100 mm diameter. So this is 100 mm at a velocity of 1 meter per second. The transmitter is at an angle, okay, and this is at an angle of 45 degree, and you may have a receiver somewhere here. It says that discuss this case with ultrasound time of flight velocity measurement point of view. Okay, so first we say that the length L from here to here will be d divided by sine theta. Theta is given here. So if this is d, this will become d divided by, so this is theta, d divided by sine theta. So that is the diameter of the tube is 100 mm. 100 mm is 0.1 meter divided by sine theta, sine 45 degree. So the length traveled by the wave from the ultrasound wave from the transmitter to the receiver is 1.141 meter. So the transit time then would become T1 to 2 would then become 0.141 divided by the velocity of sound v minus u into cos theta. So let's say this is u. So this is along this direction, u cos theta, u sin theta. So v minus u cos theta, so that is 0.141 divided by the velocity of the wave is typically sound wave within the, considering this is water, is 1500, then minus 1 into cos 45 degree. So that will come out to be 94.325 microsecond. If I place another pair of transmitter here and receiver here, then T2 to 1 is going to be 0.141. Now V plus u cos theta. So this, if I substitute 1500 plus 1 into cos 45 degree, this will become 94.236 microsecond. Now, if I want to know the time difference, delta t, because if I do delta t, then I can get this as T12 minus T21. That will give me something like 0.089 microsecond. So this is something like 89 nanoseconds. So it's a very small time for a control electronics to measure. Okay. But instead, you can use the electronics to do this. So basically, this delta T is L divided by V minus U minus L divided by V plus U, right? So you have V square minus U square. So LV plus LU minus LV plus LU. So here this LV get cancelled. So you have U divided by V square minus U square into L. Okay. So it says that if you know the delta T and you know the velocity of sound and you know L, you can actually find U. Okay. But this time is actually very small. So instead, you can do this. You can ask the electronics to calculate T12 into T21 divided by T12 minus T21. And if you do that, you would actually get this as only d by v.
Sir, hello.
Yes.
Sir, before that line, LU 2 times is there, but you substitute only U into L. It is like that, sir?
Yeah, sorry. Yeah, to you. So if you do the multiplication of these two and divide by the difference, you would see that this will come in terms of only the diameter of the tube and the velocity of sound. So if you calculate this quantity, then it will be T12 is 94.325 into 94.326 divided by 94. 236 325 minus 94.236, which is basically diameter of the tube, which is 0.1 meter divided by velocity of sound, velocity of the flow, which is 1 meter per second. So that will give you 0.1 second. So which is reasonable to measure. It is not in nanosecond. So it says that this kind of calculation is easier to measure by the control electronics than a simple difference between the signal to calculate the velocity. Okay, so if you are okay with this, now I will move on to the next question, which is on viscosity measurement.
So just a query in the previous question, sir. I'm sorry. In the second derivation, where we have measured like delta T is equal to L divided by U minus V and L divided by U plus V.
Yeah.
So basically, here we are assuming that the receiver and what I mean to say is transmitter are not in angle with the flow, right?
Yeah. This is not an angle, but if there is an angle, then you have to take the component of the velocity along the,
So basically, we have to assume that this U and V will be along that. The V
along the direction of propagation of wave.
Okay, and even the V also, V has to be taken in that direction only, right, sir?
See, the sound wave is always in this direction from transmitter to receiver.
Right.
Only the flow velocity will have a component.
Got it, sir. Thank you, sir.
Right. So next we talk about viscosity measurement. We discussed about the setup. If you remember, we had this kind of arrangement. So this space is basically filled with the fluid whose viscosity we want to measure. Okay, this annular space. So this is called the rotating cylinder apparatus for measuring viscosity, and this is run at an angular speed omega of 1800 plus minus 5 revolution per minute. And the geometric data is specified as, so this is your R1, this is your R2. R1 is 37 plus minus 0.02 millimeter. R2 is 38 plus minus 0.02 millimeter. L is 0.5 millimeter, 100 plus minus 0.5 millimeter. L is basically this thing is 100.5 millimeter. This is A, with the gap at the bottom, 1 plus minus 0.01 millimeter. What is the torque experienced by the stationary cylinder? Okay, so this inside cylinder is typically stationary. The outer cylinder is rotating. So what is the torque experienced by the stationary cylinder? Number one. Number two, what is the power dissipated? And because these values have some uncertainty, perform an error analysis to find out what is the uncertainty in the torque and the power. So fluid in the viscometer is an oil with a viscosity of 0.0331 kg per meter second. Okay, so this is the question. So how do we approach? So first, we need to know what is the torque from the formula. We had derived in the class that the total torque, there will be some contribution coming from this face and then some contribution coming from the bottom face. So this will be basically mu into pi omega R1 square into 2 R2L over B plus R1 square over 2A. Okay, so this is basically coming from the sides here, and this is coming from the bottom. What is B? B is basically R2 minus R1, the gap here is basically B. Okay, so we know omega, we know mu, we know R1, R2, we know B, we know also A. So all the parameters are actually known. So R1 is, we take the nominal value, which is 37 millimeter. R2, we take 38 millimeter. That means your B is 1 mm, because B is R2 minus R1. And A is given 1 mm, that is 1 into 10 to the minus 3 meter. This also 1 into 10 to the minus 3 meter. R1 is 0.037 meter. This will be 0.038 meter. So now we can find out the total torque. Mu is given 0.0331 into pi into omega is given. Omega is 1800 RPM into R1 square, that is 0.037 square into 2 into R2, 0.038 into L. L is 100 mm, that is 0.1 meter, divided by B. B is 0.001. R1 is 0.037 square, 0.037 square, divided by 2 into A. A is 0.001. So if we do the calculation, we will get this as 0.222 Newton meter. That is the total torque experienced by the stationary cylinder. Now we need to find the uncertainty on this.
Sir, एक सवाल है यहाँ पे, this 1800 should be converted to 2 pi and divided by 16, sir, if I'm not wrong, right?
Yeah, this is omega. You are correct.
Right.
This is in RPM, right? So this is N, not omega. That is in radian per second. Okay, so this is radian per second. So we will have to correct this. Thanks for that. That is the thing, and then that will come out to be 0.222 Newton into meter. Now we have to specify an uncertainty on the torque, because omega has an uncertainty, R1 has an uncertainty, R2 has an uncertainty, and also L, that we here L also has an uncertainty. Okay, so how these uncertainties in omega, in L, in R1 and R2 propagate to give an uncertainty in the value of torque? Okay, that is the question. So first we say that we have to know how the torque varies with each one of these parameters, right? And then we have to basically find the derivatives, and then knowing the individual uncertainties, we can calculate the total uncertainty. Okay, so first we need to find out let's say we first talk about how the torque varies with the change in the R1. Okay, because R1 has an uncertainty. So we have U of R1, U of R2, U of L, U of omega. So we have all these four uncertainties. So we need to calculate the gradients for all these cases. So what is dou T over dou R1? What is the torque expression? Torque expression is mu pi omega R1 square into this plus that. Okay. So when you find the first derivative, dou T over dou R1, you can say that here you have R1 square, so it will multiply here, it will become R1 square, and then here it will become R1 to the power 4. And so you can write this as, let me write first dou over dou R1 of 2 pi mu omega R2 L into R1 square divided by B plus mu pi omega R1 to the power 4 divided by 2a, right? So if you take derivative, this will become 4 pi mu omega R2 L R1 divided by B plus, now this will become 4 mu pi omega R1 cube divided by 2a. So all these parameters are known, right? So if we substitute, then dou T over dou R1 will come out to be 1.986 Newton. Similarly, if you take dou T over dou R2, so here you see that R2 is here. There is no R1, R2 here. So derivative of the second term will vanish. So it will just become 2 pi. So let me write down for your dou over dou R2 of 2 pi mu omega R2 L over B R1 square plus mu pi omega over 2a R1 to the power 4. So derivative of this term will be 0. So only the first term has R2. So it will just become 2 pi mu omega L R1 square over B. And if we substitute the values, we will get this as 5.367 Newton. Okay. Next, we need to know, okay, A also has a uncertainty, L has an uncertainty. So we also have U of A. So let us now find how the uncertainty in A affects the torque. Of course, when you take dou T over dou A, the first term is not a function of A, so this will give you 0. Here A is at the denominator, so that is basically dou over dou A of pi mu pi omega R1 to the power A to the power minus 1, right? So that will give you minus mu pi omega R1 to the power 4 divided by 2a square. So if you substitute all the values, it will give you minus 18.37 Newton. Okay. So we got the effect of R1. We got the effect of R2. We get the effect of A. Now we need to get the effect of L. Okay. So what is the effect of L? So we can write dou T over dou L. So you can see that L is only in the first term, second term derivative will go to 0. So if you take dou over dou L of 2 pi mu omega R2L over B R1 square, that will give you 2 pi mu omega R2 R1 square divided by B. And if we substitute the values, this will give us 2.039 Newton. So dou T over dou L is done, right? And only the uncertainty with respect to the RPM is remaining. So you can see that again, RPM is appearing in both the terms. So we will have both the terms in there. So dou T or dou omega will be basically mu pi here. If you look at here, mu 2 pi mu R2L R1 square over B plus mu pi R1 4 over 2A. So this, if we substitute the values, this will come out to be 0.00118. So now we have all the gradients and the uncertainties. We just need to find the uncertainty in T total. That is, you say U of R1 into dou T over dou R1 square plus U of R2 dou T of dou R2 square plus U of A dou T over dou A square square whole square root. So if we substitute all the values, this is 1.986 is the uncertainty in the R1 point here 1.986 is the dou T over dou R1 into the uncertainty of UR1 is 0.02 millimeter. So that is 0.02 into 10 to the minus 3 square. Similarly, for UR2 into dou T over dou R2 is 5.367 into 0.02 10 to the minus 3 square plus the UA, which is 36.736, the gradient, into U2 is 0.02 10 to the minus 3 square. Then U dou T over dou L, this term is 2.039 into 0.04 into 10 to the minus 3 square. Then we have UW, which is we have 5.367, then 18.37, 18.37 is dou T over dou A. I think this is what we missed. 18.37 into UA. UA is 0.01, right? So into 0.01 whole square. Then we have dou T over the 2.039 into UL is 0.5 mm. 0.5 into 10 to the minus 3 square. Then we have dou T over dou omega, which is 0.00118 into the uncertainty in RPM is 5. So that means U of omega will be 2 pi into 5 divided by 60. So this is 2 pi into 5 divided by 60 square, and you take whole square root. So this will come out to be plus minus 0.0022 Newton meter. So that is the uncertainty in the top. Okay.
Professor,
Yeah.
sir, we have found uncertainty of R1 and R2. So in that case, we need not find for B value, sir.
Sorry, can you tell me again?
For R1 radius and R2 radius, we have found the uncertainty values. So B is R2 minus R1, right? So we need not find separately for B value.
So if you are already taking the the uncertainty in R1 and R2, and you have the B here again. I don't think that you have to again calculate for B, because B is a function of R1 and R2. Right, so you can always write this as R1 minus R2 minus R1. Mm. Then the B. And you do not have an uncertainty actually for R1 minus R2 here. You do not know whether it is going to add up or really cancel out. So I don't think we need to really separately do for B here, because there is no uncertainty as such specified. Okay.
Okay, sir.
There is no because from the uncertainty in R1 and R2, it is difficult to predict what will be the uncertainty in B when you subtract, and because they are different. Because that itself would require uncertainty propagation.
Understood, sir.
Okay, so I stop here, and we will continue. We'll solve some more questions on the other topics that we covered. And I hope your exam is approaching very fast. I hope you all are revising the portions and solving questions. Okay, so please do that. As I said, you will find plenty of problems in both the S.P. Venkatesan book and also the J.P. Hallman book. So these two will give you a lot of practice problems, which should be.
Sir, will there be any weightage of before midsem, after midsem, in the question of final year?
There is no weightage. It is end time is always evenly distributed.
Okay, sir. Okay, sir.
Sir, in this question, power dissipated, what is the power dissipated? There is a statement. Should
So
we answer
power
that?
dissipated is basically tau into the torque into omega.
Okay.
Okay. So if you multiply the torque by omega, it is the power dissipated. And I wanted to do that, but because of the shortage of time, I'm not doing. But you can also find then, because now you know the uncertainty in torque, and you already know the uncertainty in omega, so you can also find out the uncertainty in the power dissipated. Okay.
Okay.
Recording stopped.
Thank you, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.